Okay, hello everyone and welcome to the latest Clojure workshop. Today we have Rohit talking about statistical inference, intro to statistical inference workshop. And we're going to hand it over to Rohit now. So thanks very much. Take it away, Rohit.
Awesome. Thank you, Mark. So I can start by introducing myself. My name is Rohit. I have been, doing engineer. I've been an engineer that mainly collects a lot of data. Like, I collect data for other data scientists and data engineers that, make useful conclusions out of this. But, anytime I try and run an experiment for any for any reason and then try to make my own conclusions, I am asked to go read some statistics. And it's difficult, when you want to try something and if it's true or false, but you want to make your own inferences. It's rather difficult without somebody telling you that it should be a normal distribution, or it should these standard, if it lives outside certain standard deviations, you can't use this formula or this method. So to try and learn some statistics, I came across this book called Statistics is Easy. And the examples that follow are from the book itself. And it is an introduction to statistical inference with first principles. And what I mean by first principles is that, if you can count and you can, you understand the concepts of shuffling, shuffling a deck of cards maybe. And then if you can understand that, you can derive, conclusions about experiments you make happen. You do not have, this method that we're using here. They're, randomization techniques. They're known as resampling. But by using this method, you do not need to know what the underlying distribution is. Effectively, what you're doing is you're repeating an experiment with random values many times and then recording the results. And if you can do that, you can say whether an experiment that you did with making changes to them is different from what you normally see. So if the experiment succeeded or not just by doing, just by using randomization techniques. And then, you obviously, if you are doing an experiment, you want to know how, accurate a measurement is. And when I say accurate, I will go into this. The measurement of an experiment is done using confidence intervals. You want to know the range of values that an experiment is likely to give you. So you want to answer that question, and you want to also see, if the observation you're making is, it just happened by mistake or by random chance. We'll also look at some real world applications and any other practical considerations that, we should consider when we are, using these techniques. Does anybody have any questions on the goals? Would like to see something else? I'd like to make this session a lot more interactive, since in the last session I was actually putting code together. Now that I have the code here, so we can be a lot more interactive in trying things. So feel free to, speak up or post it in a chat, or and I will try and answer these questions as we go along.
I think Jamie has posted a question in the chat about which book you're referring to.
Yes, so the book is meant, this both the notebook you see here, not the space, the page you see here is all inside GitHub, and I will point you to it. But these are the books, right? It's Statistics is Easy by Dennis Shasha and Nanda Wilson. The examples are taken from there, and the Python code is literally translated into Clojure. And if you really want to dig in, if you think these randomization techniques are really interesting to you, you can, the underlying math that goes and, you can understand why it works is in the book, Bootstrap Methods and Their Application.
Okay, thank you.
So let's start with, the standard coin toss, right? Like, is a coin fair? If I told you that, I tossed a coin 17 times and I got 15 heads. Now, it's like if you were trying to do this, people will say, or like, the regular thing to go to would be to go to a binomial distribution and, pick out sample values. But how would you ask, a 7-year-old to do this? Like if you told a 7-year-old, like, I tossed a coin 17 times and I got 15 heads, and I'm telling you that the coin is fair. The 7-year-old will go and he will toss the coin, and he will toss it 17 times and says, I got 8 heads. And then he will note it down. And then he'll toss the coin again. And then he'll say, like, I got 5 heads. And he'll write it down again. And he'll do this, and then after a while, he'll say, like, this is not possible. What you're saying is like, this 15 heads and 17 coins, this coin is not, a normal coin. So we are going to do the same thing. What we are doing is we are going to make a large number of buckets. So we are going to create a draw space. And we are going to repeatedly draw from the draw space. And we're saying that, as we are repeatedly drawing from the draw space, if I see more than, so I divide the draw space into 2 right here, right? Like 1 by P. So there is a 50% chance of heads and 50% chance of tails. Let's just take that, value of P. I'm using the value of P to divide these 1,000 buckets into 2. And I'm going to draw from the 1,000 buckets. If I draw from the left side, it's a heads. If I draw from the right side, it's a tails. So if I draw from the left side, if my draw is greater than, if my, P into draw space, which is the left half of the bucket, is greater than the draw, so then the draw is on the left side, and I increment the number of successes, saying that I got 1 heads. And, so let's try this. And, it's like, keep your attention on the left side of the browser. The right side is just evaluating this. So don't pay attention to that very much. It's just to show you that it hasn't hung really. So I did this once, I flipped a coin 17 times, fair coin, and I got 8 heads. If I do it again, I get 7 heads, and then I do it again. These are where the results are. So I'm just getting these results again and again and again. And all I'm going to do now is draw this out. Basically, I'm going to do this 10,000 times, and I'm going to draw this distribution out. A distribution is mainly just, it's a count. It's a histogram of values where, where we are counting successes. So, I'm just going to render this. It should render right there. So if you look at this graph, it says that I got 8 heads 1,800 times and 9 heads 1,886 times and 10 heads 1,500 times and so on, until you look at the 15, where I see that I only got 12, 12 head. So so basically everything on the right side of this 15 is counted as a success, really, because if I can get 15 or more heads, then that counts as a success. So 12 plus 4 plus, some small value where my cursor doesn't go. So roughly like 18 times I would have gotten fair coin tosses. So if you can see, like, this count makes it highly unlikely that, that my coin is fair. Now, if I just to verify these results, I'm going to use the Kixi stats library, which is, one of the, it's a really nice library if you want to do these statistical inference techniques. So I'm going to, just to validate my results, right? Like is this really randomization? Is this really typically a binomial distribution. I am going to use the Kixie-stats library, and I'm going to derive the same. Like I'm just going to take samples, and a samples is one run of an apply prob, really. So if I did that, as you can see, it's, it's roughly the same. Like I had 8 heads with 1893. There is some randomization involved. 1874. There is some randomization involved, so it'll be nearly the same as the graph. So the technique is sound, is what I'm getting at. Sorry, is there a question? Okay, never mind. No question. Is there a question? No. All right. Okay. So what I'm going to do now is render the both of them side by side, like both the distributions side by side. So my A of the experiment is the normal coin, what happens in nature, like you toss a coin many, many times, you make a change to a web platform where you change maybe the color of a button to see if it makes a difference to the system. And that, the A is what is the normal, the B is, what is the experiment, like what you're making a change to the normal to, for your experiment. And you're saying and you're checking if that change actually is valid or not. So I am just rendering both of the distributions side by side here. So as you can see, for a fair coin, if you did the random experiment, you would see the blue distribution. And if a coin was really unfair, like where you could see 15 out of 17 heads, you would see a distribution like this by tossing that coin. As you can see, the means of these two coins, like everyone knows that roughly you would get 8 heads out of 17 for many of the tosses. As you can see, the difference between the means is large, right? Like, fairly large. I mean, it looks like they're two different coins because they behave differently. So this coin is not a fair coin. And if you look at it, it's not doing anything different. Like it's just drawing the two trials out. One where, the probability is a fair coin. And in the other case, the probability is an unfair coin. And you're doing 17 coin tosses. Does this make sense? Is this any questions?
Makes sense.
All right. Here we go. So data scientists will typically report this, as p-values. So for a p-value, what they do is they say they state a null hypothesis. The null hypothesis is the normal boring hypothesis, and the alternate hypothesis is that the coin is not fair. And the way they report this is they run an experiment. So we're going to do the same thing. We are going to do the experiment many times. We are going to call apply prob, which was that, choose from the left side or right side many times. We are going to count all of those counts where, the observed is greater than what you see in the experiment. So anytime you had 15 or more heads, you would count that as a success. So you would take and you would just count all those successes. And then you'd see how many times you got those successes. So if we run such an experiment here, I got 0. Oof. Oh, that is the wrong experiment. I ran the wrong experiment. I went out of sync. Sorry. Here. Out of I got 8 out of 10,000 times where I got a success. So the p-value is it's just the division of 8 by 10,000, which is the observed probability of 8 into 10 raised to minus 4, which is, so data scientists will take this p-value. They'll say that this value is less than 0.05, which is less than 5% of the results show what you see as observed. So you must say that the null hypothesis is false, and hence the alternate hypothesis is true, which means that the coin is not fair. So this is how data scientists would report the success of an experiment. Like I could run this many times, and if you see, like, you will always see a value less than 0.05. And we'll come to this, when we report the power of a test, but effectively, like, it's like running this 10,000 experiments many, many, many times. Like, so you put another layer of repetition on it, and then you count it. And then you say, like, with 80% probability, this test is doing the right thing. I can predict that this experiment is reporting the right results. But we'll come to power later. It's just a preview of what power really is. So does this make sense? This is the p-value. Observed probabilities. What is the p-value? That is the probability that, what you're seeing is not happening by random chance. The observation you're seeing is not happening by random chance. That is the definition of a p-value.
Makes sense.
All right. So no questions, right? So far? Okay. So, because no questions. So one thing that, data scientists also do is that they take binomial distributions, and like I showed you here, what we are really doing is we are taking the population and representing it by its mean and then comparing the means, right? So a z-test does exactly that, but it does that for a Gaussian distribution or a normal distribution. And a normal distribution is one in where this, like a binomial distribution is discrete values, because you can have a heads or a tails. You can't have half a heads, right? It's not a continuous variable. It's mostly a true false thing, and you're just counting discrete values. So normal distribution has continuous values, which means that you will have values between 0 and 1, and you'll have decimals and floats and it's a continuous range of numbers. So a z-test basically is the comparison of two means. And again, I'm using the Kixie-stats value to do a z-test. Basically, I'm converting a binomial distribution into a normal one and then testing the p-value, right? So in this conversion, what you say, the mean of the population is 0.5 into p, and the standard deviations are square root of p into 1 minus p into like the population or size. So it's p into 1 minus p. That's why you see the two 0.5s, and the population is 17, and you take the square root of these. So this is where, like, you would go to a math book and look at these formulas and then apply it. But with this test, all you did was you figured out how to shuffle and count successes and failures. So if I ran this, you would, you get a value of 0 because it's really, really small. What is it saying? Can't take the value of macro. What? Hold on. Okay. Yeah, it's 0. I mean, it's more than it basically gives a value of 0 because it's far to the right. There are too many standard deviations. So a z-test, basically what it does is it calculates the number of standard deviations from the mean, and then the p-value is then it uses a table to see how far, what that means in terms of probabilities, and returns that value. So is this method clear? We can look at other examples that we can use, when we are, where this could be used. All right. So let's say, we have an online game company, right? Where, people typically 70 of the 100 people come back. Basically, like, they log on to the app, they play their game, and then they come back the next day. So 70% of the people, do that on the normal, in the normal scenario. And, we wanted to introduce a new feature in the game. And after we introduced the new feature in the game, we observed that 38 of 97 people are coming into the site. And, you say like, we've done all our market research. We know everything is good. And we know this is a feature that, people really wanted. Is it possible that this is just a day of the week problem? Maybe it's a holiday. Maybe it's the time when we introduce this feature. Should we be concerned, right? So let's say we run that same experiment. We are going to run this experiment where we say like, we're going to again render A/B, where A is the normal behavior and B is what you are observing. 38 of 97 showing up. And then, you ran the test 97 times. So let's say we did that. Ooh. And you see the blue is the A, which is, the distribution you should have normally seen. And if, this was true, this 38 of 97 was true, like there should have been a lot of overlap between the two. But you can see they're like completely different from each other, which tells you that there is something wrong in this feature, that this hasn't happened by random chance, that you should consider looking at that feature again. Right? And if we encoded that experiment, the same experiment, we got, 0 times this time, like where we saw that. We constantly keep getting this. You see, they're so far apart that they never overlap. You can never have that happen. So this is one place where, if you were like, conducting an A/B experiment where, some of the population ended up in the red half, it's like, and typically this is how companies would do A/B tests. They would take a feature, introduce it, and put a small amount of the population in that bucket, and then see how they do, and then count. And on the right side is what your normal is. And does this make sense? Like, this is A/B experiments, really. This is how this, binomial distributions are used in A/B experiments. So let's take another example. We're doing an A/B experiment where the normal click-through rate is 2%, okay? And so 2% of the people that are shown ads actually click into the ads. And this is, very normal for, advertisements being shown. And then the ad tech company, it changes it such that, it becomes 3%. So, they basically change how they're showing ads. Maybe, they've included how people search for things and then show the ads similar to how Google does ads. Or maybe they're looking at their customers from like their age groups and then displaying the ad based on a customer's age. But, whatever the criteria for their new selection, is it working or is it not working? Like, is it, so let's render that distribution now. And answer. Okay. So you can see there, like, there is some overlap in these distributions, but they're still, fairly far away. Like, the ones that are overlapping are, more than 1 or 2 standard deviations away. So if you report this experiment, are they different? Is this new selection system better? So in this case, the null hypothesis would be that the new selection system is not better, and you do the test and you're saying now whether the new selection system is better or not better. The blue is the normal, the red is the new. And maybe I should make the red green in this case because, it's actually a successful experiment, but so if you were to report this, so again, it's less than 0.05 of the time. So the p-value is less than 0.05. 53 out of 10,000 times I got, 3% or more. So these are some of the practical applications of a method like this, where I really didn't know what the underlying distribution was. I don't have to know what a binomial distribution is, and I can still make these experiments and report results. Are there any questions before I switch to the second method, where we're not comparing means, but we are doing a little more than that? Are there any questions that people have about
there is a question in the Zulp chat, which is when you introduce a new feature like this, what percentage of your population do you run experiments on?
Right. So that's where the power of a test comes to be. Like, a lot of A/B experiments, the sample size. So what would happen, let's say, like, if you had a small sample size and you had like, the same values, because, it was a very small sample. Let's say you put 2% of your population in this A/B experiment. It's very likely that, your sample size is small, and, what you would do is then like, look at the power of a test and then say like, my sample size is too small and I need to increase my bucket, because I can't conclusively say whether this is happening or not. It'll come, like I'll come to the power of the test, but like, that is where a power of a test is used. So if you need more sample size, you need to like reallocate your buckets such that you can get a reasonable population into the system where it's diverse enough where you can make a conclusion.
Okay, that makes a lot of sense. One more, actually a request. Can people get a link to the Git repo where this presentation is?
Yes. Let me. Oh, you would like to work through it? Let me post that then. Here. I should have probably posted this first. Should I just post it in this channel here?
Either place, I can copy it to the other. Yeah, very good.
I will also post it on the chat.
I got it. We have one more question before we move on. And that is, how does it work when testing or drug discovery feels unethical given expectation of failure? That may be beyond the scope of this presentation, but if you want to take a stab at it, go ahead. But I guess the point is, for example, what if you know there's a life-saving drug and it seems to be very effective? Do you continue on with the trial to the end, or do you actually abandon the trial and just go ahead with it?
I mean, I can answer this as I'm working through the next example, but one of the, and that was a part of the practical considerations, that, you can't be biased in how you choose your population. You can't, or you shouldn't, like, the tests are ineffective if there is human bias in the selection. For instance, if you were, considering a weight loss drug, would you consider a very fit population and then run your experiment on that population? It's, or like, do you, do you use your knowledge of the population to select the population? Now, if you are doing that, these methods, no matter what you do, will not be effective. So you shouldn't do that. And it is like ethics can be, I don't know how to state this honestly, like, but it's very subjective, right? Like how people, say what is ethical. But for the experiment itself, like you have to choose independent samples, and there has to be no inherent bias in the selection.
Right. I know that historically, some drug trials have been halted because of this very reason, but it's certainly does invalidate, the trial as it was designed. So that's a tough call.
It is. I would like to hear how people, I mean, if there are any, if there is somebody doing experiments, it would be very nice to hear how they select populations. If, me as someone who's trying to learn this space would gain, or everyone here would actually gain on how populations are selected for tests. Yep. So if there is anyone in the audience that can say how they do it, I would be very happy to hear that.
Anyone? I think I saw a hand go up using the raise a hand feature in Zoom. So if you have any other questions, please go ahead.
Yes.
Otherwise, we'll continue on.
Okay. All right. So since somebody brought it up, the drug, this is the next part of the document where, instead of like, just success or failure, what you are doing is you are recording values, like, it's not a success or failure. It's more of like, we're checking the effectiveness of the drug here, and the numbers indicate measured improvement. And, you could say 54 times out of, like this is how much someone improved by taking a placebo versus. So what we do in this experiment is we give some part of the population a placebo, which is a sugar pill, really. It has no medicinal properties. And we give some part of the population the drug. And we check the measured improvement of the placebo versus the drug. And then we say, like, the measured improvement of the drug is better, X points better than the placebo, and then hence the drug is effective. This is the experiment we are trying to consider, make happen here, right? So if you're doing a medical trial, like I said, if it's for a weight loss program, like let's say somebody lost, 54 pounds is too much, but like or it's a growth, it's a growth drug, like whatever, like, it's, 54 times better than not having anything at all. Let's just say it's the measured improvement, right? So these are like, the measured values for the drug. These are the measured values for the placebo. It's just a random population. We haven't put any biases. We're just selecting them, and we're giving some of them the drug and some of them the placebo and measuring. So what we are doing is we want to represent this by a single mean, right? Like, we want to say, like, this is the statistic for the population, and the statistic we're using is the average. And we are saying that, we are calculating the average diff in the points between the drug and the placebo. And, we're saying it's 13 points. Now, so what we have done is the average diff is we have taken the average of sample 1, the average of sample 2, and then just subtracted it and taken the ceiling of that value. That is our statistical measurement of the difference between these two populations. and we say like, the drug is 13 times better than the placebo. Like, it's 13 points more effect, or 13 times more effective than a placebo. And hence the drug is effective, and we want to do the next set of trials. Now, how do you know this 13 was not seen by random chance, right? So how do we, make sure that, we are measuring this, we are seeing that this did not happen by, random chance. So what we do is we run an experiment where we shuffle the labels, okay? And we check the average difference for each in each of the instances of the shuffled drug, like, drug and placebo. And each time you see a value greater than 13, you increment a counter. I will come to why we shuffle it, but we will come to like, how shuffling, like, actually makes this happen, and why this is a true experiment. But for the moment, we'll just focus on the process itself. So all we're doing is, in the shuffled average diff, is we are putting the drug and the placebo together, the sample and the population. So we put it together and we shuffle it. Okay, so right now these two arrays are together but shuffled. Then we take these many values from the shuffle and call it the drug, and these many values from the rest of them and put them in the placebo, and then calculate their average differences. That is all this method is actually doing. No more than that. So let's do one run of that in the shuffled average diff. And you see a difference of 1. And you see a difference of 4. So what we are doing is, every time we see a value of more than 13, we are going to count that as a success. It's similar to like, like the heads and tails experiment, where every time you see more than 15 heads, you count a success. And every time you see less than, you discount it. So that's all we are going to do in this experiment. We are going to do this shuffled average diff many times. And we'll keep doing it, and then 10,000 times, and then we will just record it every time. So if we drew a distribution of that, this is what that those trials would look like. Most of the times it's 0, like there is no difference between the average of the drug and the placebo. And if you look at it, 13 or more times is like here. So it's 12 plus, yeah. So everything on the right side of this, you sum them up, right? The y's, and that's how many times you got 13 or more point differences between the drug and the placebo. So I'm not going to sum this up, but it's a very small value compared to the 10,000 times you ran this experiment. So if you did that, like, again, we are going through the same process of like reporting results. What we are doing is, repeatedly you're finding the shuffled average difference. And every time you see it's greater than the observed difference, you like, you're just counting those. You're filtering all where it's greater than the observed count, and those are the count good. And then you're just dividing the count good by number of bootstraps. And that's how you're reporting the results. So did you do it? Okay. So it's saying like, the probability of this happening is, you seeing a 13-point difference between the drug and the placebo is 0.002, which is less than 0.05. Hence the drug is effective, and you can move forward with this test. Does the experiment and the, how it was set up and what is going on in there, do the mechanics make sense? We will go into the reasons shortly of why we do this shuffling.
Yes,
Okay.
makes sense.
Okay. So typically, if you did this using um, standard statistical methods, you would use a t-test. And the reason you use a t-test is because you have a relatively small population, and basically like you don't know what the standard deviation will be, because this is a new drug. How are you supposed to tell what the average is and what the difference between? So typically you would go and use a t-test. And if we ran the same thing again, I'm using Kixie and Kixie is this really nice library that like one of the authors, Henry, like helped me put this together just for me to validate my process with what is happening with Kixie. And the Kixie report this t-test as, I guess, that 0.001, right? Like, basically, if you ran this experiment, many times, you would probably see that. Is it executing? It does, yeah. So like, it'll fluctuate. Like you can see, like it sticks around the values, but like, there it is. That's cheating right there for you. All right, so let's go to why we are doing this shuffling, right? So what we are saying is, if the drug has no real effect, then we can say that we would notice that the placebo can often give more improvement. So what we are doing is we are taking some of the placebo measurements and we're putting them as if they were drug measurements. And then we're saying, if even if we did that and we're still seeing an observed value greater than 13, then the drug really has no effect. Like what you observed here is just by random chance. So maybe you should get a larger population and try this, or consider doing something with the drug itself. So that is why we shuffle, how we like that is why the shuffling works. Basically all we're doing is we're taking some of the placebo measurements and reporting them as if they were drug measurements, and then checking the difference between the two. So let's take a degenerate case, right? Like I just randomly take some distributed values of the placebo, and all I do to the drug is add 13 points. Same, you should effectively see the same kind of result, right? Like, if the test was, if the way we are setting this experiment up and checking the differences, if this wasn't right, then we should see the same result. Like we should say even this experiment should return a true, where we can reject the null hypothesis, right? But if we just draw out the distribution itself, let's draw out this distribution. This is what you start noticing. If you notice, like many of the times you like, you see 13 is like somewhere like you see it's right in the middle of the like 13 is somewhere close to the middle. So roughly 50% of the times I got more than 13 this 13-point differential. So although I cheated, and when I cheated, like it basically changed the shape of the distribution. And if you see these ranges, they changed completely compared to, I'll go back to this one. This is the original test. So you can see, like it has gone completely different. I chose random values, and if I were to report like the result of this experiment, I say 42% of the times I see more than 13. So the null hypothesis is true. that the drug is, the same as the placebo. There is no difference between the drug and the placebo. So far, so good. Questions?
Yeah, it looks good. This is all making sense. I have a slightly tangential question, I guess, which is that we've seen some of these distributions are bell-shaped and some are distorted or offset. And so I'm a little confused on the terminology. When people talk about a normal distribution, does that seems to be sometimes synonymous with the bell shape.
Right.
And sometimes the binomial distributions are bell-shaped and sometimes they're not. So is there?
So it's just where the mean is. Is the mean 0 or not 0? Like, binomial distribution. So like, if you look at this, these are all binomial distributions, right? Like,
oh, so they're always bell-shaped, binomial?
Yes, but they are like, because you're running the sample, so you're going to get an average because your statistic is the average. So, you're always going to have an average and you're going to have standard deviations, and you're doing this, there is some representation of the population in a number, and we're saying that statistic is the average. So, if you have an average, you have the left side and the right side, and typically you see that bell shape. It's just where the 0 is mostly. Like this is this odd shape, right? Like where it is, slightly to the right. The distribution is, slightly to the right. The distribution you see here on the red side.
But it still has that same
Yes.
shape of the distribution.
Yeah.
Okay.
It's just compressed, and it's so the only difference between the binomial and the Gaussian is one is continuous values, one is discrete values, because you're counting successes and failures in one, and those can only be, true or false. It can't be, there's no gray there. So
right.
So in both cases, you'll see the same shape, but in one case, you'll see a more continuous value. In the other case, you'll see more discrete values like this. You'll see histograms.
Excellent. Thanks.
Okay. So let's go to the next one that, this is a measure of effectiveness of an experiment, right? So is the drug effective, right? And what we're saying here is that, let's say, the average survival on the placebo is 5 years. And let's say the drug increases that survival by 3 days. And now, 3 days might be significant. It might be very, very unlikely, like, when we're doing our shuffle experiment, that you will get a 3-day difference between the lifespan. But, it's 3 days. So is it really worth, moving forward with this drug, right? Like, is it really worth it? Like, of all the, will people really get this drug for, like, increasing the lifespan by 3 days? So the measure, like, the range of values that are possible with the confidence is where we use confidence intervals. They tells you, like, 90% of the times, typically 90% is used as the confidence intervals for experiments, and 90% of the times my values will lie between X and Y, and that's how confidence intervals are reported. So the measure, so one is like, is the test significant? Like, is the observation I saw happening because of some mistake or random chance? And the other thing is, like, what are the range of values that I can expect from such an experiment, from this observation? So that's where we use confidence intervals. So what we use is a bootstrapping method, which is choosing randomly at uniformly at random with replacement. So what we do is Uniformly at random means like you will, let's say you take these values, right? You draw out 348. You put 348 back in the bucket, and then you again pick a number, and that number could again be 348 or one of these other numbers. And you do this for the size of the sample. That is basically uniformly at random. Okay. You do this both for the drug and the placebo. This time you don't shuffle the drug and the placebo. You're just randomly picking values from the drug bucket and making it the size of the drug bucket. And you're randomly picking from the placebo and making it the size of the placebo bucket. And then you're just, comparing the averages and recording the value, the difference between them. So if you look at it, the confidence interval, the percentile is the 90 percentile. The edges, so if you say 90 percentile, what you do is you cut off the lower 5% and the higher 5%, and whatever the values are at that edge, the 90th percentile and the 5th percentile, that's your min and max, that's your confidence interval for the min and max. So how this works is like you find out where the edge is based on whether it's a one-tailed or a two-tailed experiment. A one-tailed experiment is, let's say, for instance, if you were measuring average order values, you will have 0 or more. You can't have negative values, right? Let's say you were doing an experiment where you were calculating order values. And it's a one-tail test because you can only have positive values. So so your 90 percentile changes. But that's a one-tail test versus a two-tail test. In our case, we're going to do a two-tail test because you can have negative, when you compare these averages, you can have negative values and positive values. So we're doing two-tail test. So we find the lower index, which is, so if I said this value here was 95.95, so 1 minus 0.95 is 90 percentile, sorry, minus 1 point, so it's 0.10 divided by the tails, which is 2, which is 0.05. So I take the number of bootstraps and multiply it by 0.05. That will give me the lower index, and 0.90 will give me the upper index. Yeah, the 1 minus point, so the 95 percentile, right? And all I'm doing is I'm taking the same bootstrap average method I showed you here, and doing it for the drug and the placebo, sorting it. And once I sort it, I will take the value. And I'm doing this experiment 10,000 times. So I will take the value at the 500th index and the 9,500th index. And those are the values that are my confidence interval. So the confidence interval for this test is, so the values vary between 7.7 to 18.24. So to remind you, this is the values between the drug and the average difference between the drug and the placebo can vary from 7 points to 18 points. This is the range of values you can expect. So now what you can also say is that there are no negative effects of this drug, right? So even if it is in the worst possible case, you should expect to see like 7 points between them 90% of the time. So it's still a worthwhile drug worth pursuing. Okay, if I rendered those confidence intervals, it's the same numbers just rendered. It's somewhere in the 7 to the 18, and then the median is sitting in the middle somewhere here, which is 13, somewhere at the 13 points. Does all of this make sense? This graph is just a rendering, so ignore all this. This is just, rendering the confidence interval like this. Before we move on to, what power is. Any questions?
Sounds like we're good.
Yes.
I have a question.
Excellent.
Hello, sorry, I was late in the meeting,
No worries.
but I fork the GitHub.
Yes.
I'm trying to run, but it doesn't look like your screen. It's just I think in the number 5 of the README, reevaluate the namespace after making a minor change. What is this minor change?
Just add a comment and save the file. Like, put a semicolon in your file and save it.
Okay.
And hopefully you should see all of it without the results.
Oh, just a comment.
Yeah, just make a small change, any change, like just put an empty space and save the file.
Okay, thank you.
Hopefully you can see it. If you can't, I can try and walk through it. We can do it after the workshop.
Command S, and let me see. No. Oh yes, you're right. Thank you.
So this is an experimental tool. This is a really wonderful tool that the SkyCloj community has been working specifically, like Daniel, who is hosting some of these sessions, is the mastermind, I would call, behind this tool, NodeSpace. And if you want to learn more, I believe he's also hosting another session sometime in the future. So if you like this tool or you want to learn more about it, I believe he's going to be hosting a session about it. Okay, let's go to power. Now, the power is, like I gave you a brief introduction of it before. The power of a test is the probability of rejecting the null hypothesis when it's false. Now, so the null hypothesis is the boring hypothesis, and if you are going to reject it because you've made some changes such that you're seeing a visible difference, you want to reject the null hypothesis. Basically, you want to call the experiment a success. Now, this in statistical inference terms is what is it? It's a type 2 error. So you're trying to avoid type 2 errors. So false negatives are type 2 errors. False positives are type 1 errors, right? So you're trying to avoid type 2 errors, and that's where the power statistic is used. The power statistic is also used to see if you need to increase your sample size. So like maybe you collected too small a sample, that's why you're not able to reject the null hypothesis. So you need more samples in your test. So how is the power of a test calculated? It's really simple. What it's doing is, if you remember a little bit earlier, I ran these I ran this experiment again and again, right? And I was, these were slightly different values every time because of the randomization and the shuffling that we are using. And what the power of the test is doing is exactly that. It's just running this experiment, many times, and noting each time where the p-value is less than 0.05. Okay. And if it, so you can say that the power of the test, like here, now this is slightly slower and I need to make changes. So bear with me if this, takes a while to evaluate. So let's say I run this one, right? Like I want to say like, can I reject the null hypothesis with 80% probability? That's the statement I want to make. So what am I doing? 1,000 times I'm running my experiment, that experiment that, we coded up earlier, right? We're filtering only those where, my p-value is less than 0.05. So if you notice that experiment, going back here, returns 3 results, right? We are taking this value, observed probability, and filtering those where it's 0.05, like less than 0.05, less than or equal, less than. Yes, where we're saying it's less than or equal to 0.05. Okay, we're just filtering them, we're counting them, and then we're dividing that by 1,000 really. So, this is, ignore this last line, right? And this is saying like, either I'll report the power of the test or I'll return a true false if I can say 80% probability. So let's calculate the power first of the original test. It will not show. Okay, that was a mistake. Okay, it's evaluating now. And because, this is 1,000 into 10,000 times. So it's a rather large value. So it takes a little bit of time to get this value out. You'll see it eventually. It'll show up. I hate doing this one because it really messes up the presentation. But if you notice here, I've also been using PMaps, trying to get it to run faster, basically conduct multiple experiments at the same time. So PMap is this Clojure feature. It's like a map, but it runs them in parallel. It does the transforms in parallel. But even then it's quite slow, as you can see. It takes a little bit of time. Oof. Can you still hear me? I just got a message saying, yeah, okay. So it says 1, so it's basically saying it's 100%, like, this experiment is like going to be 100% successful. And this is the other part of it where it returns true or false, 80% with a day. I won't run that because it takes a long time. Questions? Does this make sense?
So the 1 must be a rounding of some very, very small number?
No, the 1 is basically 100%.
Okay, so in this case,
So 100% of the
fails.
times my value was less than 0.05.
Okay.
Like the difference. So let me state this. For the original drug experiment, 100% of the times when I did that, the shuffle test, my observed difference was the number of times I got 13 or more as the observed difference was more than 95% of the times. In this case, 100% of the times.
Okay, got it. So it's not representing any given run, but
no,
how often a run is significant.
Yes.
Which is always in this case. Okay, great.
Yes. So if you look like, again, like, we ran the experiment 1,000 times, right? And we checked each time if it was significant, and, we counted them. And then we divided that number by 1,000, and, 1,000 out of 1,000 times we got that value. So we returned the value 1, which is 100%. So you can be 100% confident that, this test will not give you a false negative.
Great, thanks.
Yeah, that's what this one means. So if you look at it the other way, what you can say is I only care about, if it's more than 80%. I don't care. I don't want 100%, because maybe my sample size will be very large and I can't get 100%. I want at least 80%. So in that case, what you do is you provide, how many times you want to see success, and the power function returns a true or a false. Again, this is all pure Clojure. There is no formula in here. Power usually has this really complicated formula where then, the experiment is encoded. And, when you encode the experiment, you're expected to know what the distribution is. This is just counting. That's it. It's just running the experiment 1,000 times and counting. So let's look at some practical considerations, right? Like, when we are running these tests. Now, this part is a little bit, I need to analyze this. So there is a problem in this, what you will see after this, but, as a precursor, like, let's say you're evaluating whether college education affects salary, whether, you're trying to determine if college education affects salary. But then you have Bill Gates' salary, which is $1 billion. So assuming all these salaries are in thousands, you have one of these guys sitting here. And then you're just taking the average salary of like those people that had a college degree and those that did not have a college degree, right? And then you're trying to say like, the college degree actually makes a difference. But, because, some outlier sits there, you you make a mistake in your experiment. So one of the practical considerations is like, to deal with these outliers. So what you can do is, the way we did our picking of the 95th percentile, you can sort these values and pick and take out everything that falls, on the extreme right or the extreme left. In some cases that might work. In some cases that might not work. But this is one of the considerations you need to consider when you are doing these tests. Outliers are hard. Outliers always cause a problem. So you have to have like a method of dealing with these outliers. One way is like, just discard them. The other way is basically, instead of using the actual values, turn these values into ranks and consider using the difference between the ranks now, instead of like their absolute values. I haven't done this for this workshop, which I plan to encode it in this workbook. And when I do, I will just post an update, but I haven't done that yet. But typically, like, does college education affect your wealth or your potential earnings? Is you would use the rank transformation of the salary. Does all of this make sense?
What is the rank transformation? What does that
So
mean?
what you do is, so let's say, you sort this. Let's sort salaries. Sort salaries. And then let's say, like, I just say map indexed. Oops. Let's say I do like, basically I just going to sort the salaries and do a map indexed, and the index is the rank. And instead of using the actual values to come now, so if we did the drug and the placebo test where we subtracted the average of the actual values, you subtract the average of the ranks. So I is the index and V is the value, which I don't really care about. I return I. something like that would be the rank transformation of. Okay, sorry, save it.
So the rank is like highest salary, next highest, next highest.
Yes. And then, you do the same thing, like, so if you split this up, you just take the ranks, and then the average ranks is what you use. You instead of using the actual values, now you're going to use the rank of the people. And you're going to just take the average difference between the ranks. That is the ranked, if you were to rank the salaries, that's how it would show up. You can also, let's just put the salary also. Yeah, so like that's the rank. I mean, higher the rank, the more the salary. Whichever, both will be the same, right? Like if you were doing the difference between salaries of those. So it's like the drug versus the placebo, where the drug is, with college education, the placebo is without college education. You combine them first, take all the ranks, then split them back up, and then start using the ranks. So outliers are always a problem. So this is one way of like dealing with outliers.
Great, thanks.
So this is, all the things I've, wanted to mention. I only mentioned 2 of the many techniques that are actually in the book. There are others. There is the chi-squared, which is the next popular one, other than, just comparing of means, where you have like data for multiple categories, and you want to test the independence of 2 variables. So think of the coin experiment and replace it with the dice. How would you do that? You could use a chi-squared test, right? Like where you have 6 possible categorical values, and you're trying to see if, you can see that, like let's say you throw a die 10 times, and it's like how many times do you see a 1, 2, 3, 4, 5, 6? Like let's say you had that experiment, you would probably use a chi-squared test. So all of that, all the mechanics are in how you shuffle the values, right? Like it's just about, shuffling rather than the actual mathematical formula that goes into the chi-square. Or let's say you are comparing, if wealth affects health, right? Let's say you had a tabular column of, recorded experiments where you would look at, you would take a person's worth and you would put him in one of the, 3 or 4 classes, saying, and then, is he healthy or is he sick? And, you wanted to conduct this experiment, and you want to show whether, that wealth affects health. Something like that would use a chi-squared. Then there is, tests like Fisher's exact test is one where you have less than, you just have four possible values, and you're trying to say if it's true or false. That test came from, so Fisher, had a colleague who could predict, whether milk was poured first in tea, or it was, tea was poured first, like, and basically by tasting that tea, they could tell whether milk was poured first or tea was poured first. So it's like, it's like there are 4 possibilities, tea is poured first and it's true, and tea is poured first and it's false. So it's a very small test, but how do you make sure something like that is true? So it, something like the Fisher's exact test works very well there. There is ANOVA, which, it's like you have more than just two groups now, like, in the health versus wealth example, like, you had just two groups, sick, those people that were sick and those people that were healthy. But let's say you have more than two groups, that test turns into an ANOVA test. We know what linear regression is, it's just the prediction of the future values, correlation. The most interesting one in this book is multiple testing. Now that's the last one. What if this 0.05 was like, normally occurring in nature, right? Like when you do gene tests, when you do this 0.0, this 5% deviation, you would normally see in nature. It's not something that is, false. So multiple testing goes into methods of dealing with tests where you will normally see those error rates in real life. It's not happening because of an abnormality, but that is normal. So if when you do gene tests or, in like other fields where this normally happens, multiple testing is something that, is a technique that you can use. The book goes, and that is probably the most interesting part of this book, really. And these are practical considerations, like, we mentioned some of them during the workshop, So, when the sample size is small, you will underestimate the size of the confidence interval, and then you should probably use significance tests. So in the degenerate case, I did not go into this, in that, if you take the degenerate test of the drug and the placebo, and like say you just have one sample in the drug and one sample in the placebo, your confidence interval, 95th percentile, will always be 13. Or let's say it's just 45 and 48, right? But if you did a significance test, at least 50% of the times you would see that difference. So it doesn't really count, So when you have sample sizes that are really small, use confidence intervals carefully. So first do the significance test, then, check confidence intervals. You can use all these tests for as few as 3 points. Like I said, like Fisher's exact test uses it for 2. There are many, you can use pure shuffling. You can use shuffling with, like, drawing at random. You have all those examples. If you want to go into the details, you should, probably look at the book a little more. And I already mentioned outliers. We talked about, if the sample is not representative, like we talked about the ethics for the drug test. So, it should be a representative sample, like, a population truly means random people. It shouldn't be used, like you shouldn't be biased in your selection. And then finally, resampling, the one that draws uniformly at random. You shouldn't use that when there is, let's say you're trying to analyze stock data, right? Like, where the previous value of the stock affects the next value, that you see in the tick, for whatever reason, and it exhibits this. And let's say you're trying to draw some conclusions about that experiment, saying, let's say volume, like the volume of the stock affects the price of the stock. That test will usually fail if you just do this sampling, because the previous value, the next value depends on the previous value. So if you wanted to do tests like that, you have to take large samples of time series data, and then you can use resampling. I believe I am at the end of this. Are there any questions? Would people like to see? I am going to go through the book. I have my own personal repository where I'm going to be coding up all of the rest of the examples, like all of these other tests. And if, people are interested, I'll just keep posting in the same Zulp chat for that repo. But, this is, I'm still, I'm going to go through it because it's fairly interesting for me.
Yeah, I think that'll be very much appreciated to see you work through even more examples, and people can follow your lead and learn from them. I had one question, kind of a general question, about the nature of this book, Statistics is Easy. I found out recently that the world of statistics is kind of divided into at least two camps, the Bayesians and the frequentists. Are these techniques in the frequentist category, and is the book really exploration of the frequentist style of statistical analysis?
That is correct. So if you noticed, all we're doing is counting.
Right.
You know, this is totally a frequentist technique. We are counting. You know, we're doing the same thing. 10,000 times. We're just counting. So this is the definition of a frequentist, like a form of exploration. Whereas the Bayesian one says, whatever happened in the past affects the future. In this case, every experiment is independent. You are drawing, every experiment independently, right? Like you're not using prior knowledge. It's
okay.
So this is 100% frequentist form of experimentation in statistical inference.
So it seems particularly amenable to computer-based analysis.
Yes, that is correct.
Cool.
That is.
So do we have any more questions, comments, observations, thoughts from the rest of our participants? Here we go.
So I have a question. So some of these things could be done with like a Bayesian approach for like the A/B testing. Are there plans to add that to this package?
What package was that? Sorry.
So to, I guess,
Kixie stats, I believe.
Yes.
Oh, okay. Okay.
It does have some of the distributions, basically. I'm still not I am very naive on the Bayesian methods. So I know that, basically Bayesian methods tend to use like an existing distribution and somehow say if these observed values come from that distribution or not now. And they use, probabilities to say whether it's the same distribution. Like, I really don't understand it, and I'm probably stating this wrong, so discount anything I say, but Pixie Stats does let you draw out distributions.
Okay, thank you.
And there is, I don't know if Daniel is doing another workshop on Bayesian methods, because I know he was exploring it. But if it is, that's a really interesting topic. That's something I'm also really interested in.
Excellent. Anyone else? Going once. All right. Well, let's wrap it up then. I would first of all like to thank you very much, our presenter, Rohit Thadani. Really interesting topic. I think this will give people a great head start in exploration of these statistical analysis techniques, and a benefit to the Clojure community. I think we should also recognize many of the library contributors who have made some of this possible. For example, Hanami by John
Yes.
Anthony, Kixie Stats, Henry Garner, I believe, was the main contributor
Yes.
to that. And of course, all the Clojure
Node
contributors.
space. Let's not forget node space. The display,
Absolutely.
the node space. What you see here, like that, the Clojure community has come quite a way of using the REPL in really interesting ways, where you don't leave your editor and you can still have this really nice way of presenting results. So
Totally agree.
it's not easy.
Daniel Slutsky has been our tireless champion, creator of NoteSpace, and really making possible this entire series of workshops. He is the main driving force, and we owe him a great debt
Yes,
for all he's done.
thanks. This
So-
is, it's definitely making like huge strides, closing the gap, making it possible for data science to be done in Clojure.
It's come such a long way in just, I don't know, the last 6 months. It's quite impressive. And I think a lot of that momentum and excitement in the community can be attributed to Daniel and some of the creators of these really exciting libraries in Clojure. So with that, I'm going to stop the recording. So say goodbye, everybody, and we'll have a brief postmortem after the recording.